We're ready to rock and roll. All right. So we're going to do a little bit of a review. If you have not completed your vocab cards, you need to be working on those as well. Those are due tomorrow because they are your Unit 1 vocab cards. You will also have a very short vocab quiz tomorrow on some of those vocab terms. Okay? We should know them though because we've seen them throughout the material that I've been going through. Okay? So one of the first things that we talked about last week was the Big Bang Theory. Does anybody know what the Big Bang Theory is? I know it's tough not being face-to-face for a whole week. I wish that I saw all of my kiddos in the same week. Big Bang. Nobody. All right, so Big Bang means that there was this tiny dot, they say, and then there was, what? Yes, there was an explosion, and then it expanded. Okay, so that's what the Big Bang is. Then we talked about some things like rotation and revolution. Does anybody know the difference between rotation and revolution? So this was something else that you had to do a card sort. Rotation is what? Y'all have a test on Wednesday. I'll give you a hint. Rotation versus revolution. One of them is 24 hours and one of them is a year. Which one's 24 hours? Yes, baby. And then revolution is the opposite, which is a year. Okay, so 24 hours is rotation, that's day and night. And then revolution is an entire year, which is around 365 days. Okay, if it's not a leap year, right? And then that is why we have the actual seasons. Okay, so rotation, revolution. Something else we talked about last week was the nebular theory. And does anybody know what a nebula is? What's outside when it rains? In the sky? Clouds. So it is a gaseous cloud or a big ball of gas. Okay, that's what a nebula is. Some other things that we talked about were barycenter, precession, nutation. Alexander, you answered those last week. Do you remember what they are? Barycenter? You remember? It's okay if you don't remember. Ah, nicely done. Okay, that's a great way to put it. Let me hear it in your words.
It's two objects
So there's a point in the middle that balances. Does it always have to be directly in the center? No, okay, that's barycenter. What about precession?
change the directions of Earth.
Okay, it's okay if you're looking back, that's okay. Your answer is all right.
The direction of the axis.
Okay, and then what about mutation?
It's the walking around the axis.
The wobbling, that's right. Nicely done. Then we talked about the planets. How many planets are there? Eight. Okay. There's 4 inner, 4 outer. What's the planet closest to the sun? Begins with an M. Mercury. Nice try, there we go. Okay. Mercury. What used to be a planet but isn't a planet anymore? Pluto. Pluto. Okay, do you know why? It is, but do you know why it's not considered an actual planet? This was in y'all's notes too. Say what? No, not quite. So remember, there are 3 things. Three things that they have to have in order to be considered a planet. Somebody peek at your notes and tell me what Pluto does not have. It's okay to peek. Wrong one. So it has to have everything pushed out of its orbit, and it does not do that, so therefore Pluto is not considered a planet. Something else we talked about were Kepler's 3 laws. The 2 that you need to be most concerned with are the first and second. You had a little activity to do on those. What are the first and second? The law of what and the law of what? The law of what?
I don't know how to pronounce that word, motion.
Law of planetary motion. Okay, and the second one is? But what else are they called? What's the first law? What's the first law? That's not it, but. Bless you. If you don't know something, what can you always do? Or, if you have a device in front of you, use what? Your notes, or what else? Look it up on there. Google! Google! I want y'all to talk to me. You're here face to face, not sitting in front of a computer at home.
Explains that financial overview of sun and stuff. The resultant shape will be ellipse and special curve towards the sum of the distance from every point on the curve to two other points.
Perfect. So an ellipse is like an oval. Okay? So when you're talking about north, south, east, west, the equator, which runs which way? Horizontal. That's going to be longer, slightly, than going from north to south. Okay? All right, law 2. Tell me what it is. You got that one up too, Jake? Tell me.
States that when the moon is moved so that the mountain and the sun face a focus sweeps out equal areas at equal times. Is astronomy thus meet question and critical with the otherwise very difficult problem.
Perfect. Okay? So we need to be familiar with laws 1 and 2. Can you repeat law 2? Louder. Just say the first part. Loud and proud.
State that when the moon is able to step around the planet and the sun plays a focus sweeps out the earth.
All right. Does anybody have questions? All right. So we're going to talk.
Hold up. Is that's what I take from me and all these different notes?
Yep. And then what we talked about today. And then that's it. Tomorrow we'll spend some time reviewing. And then Wednesday will be your test. Okay. All right. So today we're going to talk about the sun. But before we get into that, the first thing we need to know is matter. So this is a little bit of the basics of chemistry. Okay. So anything that has mass and volume is matter. There are solids, liquids, gases, and plasma. So solids have a definite shape and a definite volume. Give me an example of something that would be solid. A what? Okay. Ice. Okay. Then we have a liquid. Liquids don't have a definite shape, but they have a definite volume. So give me an example of something that's a liquid. Water. Okay. Gases have no definite shape and no definite volume. Give me an example. Be specific. Carbon dioxide, one. We don't breathe that in though, right? And what? Oxygen. Perfect. Okay. And then last is plasma. This is a gas in which a certain portion of the particles are ionized. So there's no definite shape or volume. Where can we find plasma? In our blood. Right. Nicely done. Okay. All right. Next, we're going to talk about elements. Elements are substances that cannot be broken down into a similar substance. Where do we find the elements on the what? Well, there are definitely, but what can we go to look at and see them all on? Yeah, what's it called? It is a dirt. Begins with a P. Yes, tell me.
I gotta look where it's a periodic table.
Yes, a periodic table. Nicely done. A periodic table. How do you make this work? Oh, I put it on top. Thanks. All right. So some examples are oxygen, hydrogen, chlorine. We see helium, and the list can go on and on. Okay. Nitrogen. So there are 115 known elements, and 92 of those actually occur naturally. Next, we need to be familiar with an atom. Okay, this is the smallest part of an element that has all the properties of that element. So there are subatomic particles that make up the atom. Those are electrons, protons, and neutrons. So electrons are negatively charged, protons are positively charged, and neutrons don't have a charge because they are neutral. So think neutron, neutral. Okay, proton, positive, PP, and then electrons are negative. Next, we need to be familiar with the structure. So there is a nucleus which contains the protons and neutrons. So protons are what charge? Positive, and neutrons are? Neutral. Neutron, neutral. Okay, we got it. Okay. So therefore, the nucleus, because it has positive and neutral charges, it is overall positive. Then there is what is known as the electron cloud. So this is where the energy levels are inhabited by the electrons. And electrons have what charge? Negative. So that means that the electron cloud would have an overall negative charge. So nucleus positive, electron cloud negative. Okay? The next thing we need to know, and this is super important because this is where we get into the actual sun, we need to know the difference between fusion and fission. So fusion is when we combine atoms, so we're putting things together, okay? And fission is when we are splitting atoms. So that means we're cutting them in half, okay? So in fusion, we're making a larger atom because we're putting things together, so think that we're building, okay? And then in fission, we're getting smaller atoms because we're doing what? Splitting them, okay? So think if you have, does anybody have little brothers or sisters in here? Building blocks? Have they ever played with building blocks? Yeah. Y'all played with building blocks at some time in your life?
Yeah, I know.
All right. Okay, so if you have a couple building blocks put together, and then you were told you had to put them away, what do you have to do? Take them apart. Okay, so we're doing what? Splitting them. Okay, so that thing fission. And then if you just brought them out and started putting them together, what are you doing? Combining them, putting them together. So that think fusion. Okay. Something else about fusion that we need to know. This fuses hydrogen atoms into helium atoms. So this is what is actually in the core of the sun. And where would we find the core of the sun? In the what? In the middle, right? Think the core of an apple. Where do you find the core of an apple? In the middle, okay? Whereas in fission, we use uranium atoms to begin a reaction, okay? So an example of this is a nuclear power plant. Have we all heard of a power plant, a nuclear power plant? Okay? Fusion, also higher temperatures are created, and in fission, this creates radioactive waste. Does anybody know what we do with radioactive waste? No? So there are different facilities all around. I wouldn't say that there is a ton, but there are different ones found in different locations, and that is how they have to dispose of radioactive waste. Okay? So this is the difference between fusion and fission, but something that we should know is that they both release energy and they both use atoms. Okay? So they both release energy and both use atoms. Any questions on that? So fusion, together, fission, splitting it. Perfect. And then fusion, think the sun. Fission, think the nuclear power plant. So here's an example. So nuclear fission, we see that we're doing what? Okay. Fission, splitting it apart, that's right. And fusion, we're doing what? Combining it, okay? And putting it together. All right, next we're gonna talk about our actual sun. So this is made up entirely of plasma. So this is a gas that shares electrons. Its average rotation, okay, is 27 Earth days. Its surface temperature is about 5,500 degrees Celsius, pretty hot, and its interior temperature is about 15 million degrees Celsius. That's pretty hot, right? Yeah? So this is where fusion takes place. Okay, we'll come back and we'll watch this little video before I set y'all loose. So here's just a picture, so you can see the outside of the sun, the surface, and then the different layers. So sunlight, okay, that's what comes to where? To us, to Earth, right? Okay, so the sun radiates energy into space, and this energy is called electromagnetic energy, and it travels to Earth in the form of radiation. So the term radiation simply means that the energy travels as rays. So radiation, rays, and it travels in straight lines, okay? So the sun radiates energy into space, electromagnetic energy, and travels to Earth in the form of radiation, and radiation energy travels in rays, okay, straight lines. And then last, we've got the electromagnetic spectrum. We've heard of this? Yes? Yes? Maybe? Okay. So there are many different types of electromagnetic energy. They are differentiated by wavelength and frequency. Okay, so if you look down at the bottom, you see gamma rays, X-rays, ultraviolet known as UV, visible, infrared, microwave, and radio. So you see that the wavelength starts what? What do you see over here? Well, what are the wavelengths? They're farther apart, right? And then what happens over here? They get closer together, okay? So all together we call them the electromagnetic spectrum, which you see in the diagram. And the sun mostly emits ultraviolet, UV, visible light, and infrared. So UV rays are what come through, right? Are they good for us? No, okay? Because if the sun is shining, and even on an overcast day, what can we get? Sunburn, right? Okay? And I'm sure we've all seen or heard of an X-ray, right? Has anybody ever had to have an X-ray? Yes. What do they do when you get an X-ray? What do they do? Even if you go to the dentist, you gotta get your teeth X-rayed, right? What do they put over you? Yeah, kind of like a shield, a lead vest, right? And that's so that those rays aren't going to other parts of your body, okay? One more thing, sorry, I forgot. High energy particles that flow into our solar system are known as cosmic rays. So these are most deflected by Earth's magnetic field, and others interact with Earth's atmosphere and collide with molecules in the actual air, okay? So these are cosmic rays. And then solar energy for life on Earth. Life on Earth relies on solar energy from the sun. So plants transform solar energy into chemical energy through a process called photosynthesis. Have we heard of that? So who does that? Plants. Okay, so plants perform photosynthesis, and this is the way that they make food for themselves. And then we eat the plants or eat the animals that actually eat those plants. Okay, so we've heard of solar energy. Because there's a new thing now that they're doing what? Anybody with houses? Solar panels, right? So it's pretty what up front? A lot of money, right? Up front, but it's supposed to do what later? Save you money later. So even though the cost is there up front, it's supposed to save you money later. So because what is actually controlling You're the sun, okay? All right, does anybody have questions? Speak now or forever hold your peace. No? All right, we're gonna go back and watch this quick YouTube video, and then I will set y'all loose.
Writing's not that easy, but Grammarly can help. This sentence is grammatically correct.
We are at the edge of a spiral galaxy, far from the galactic core. This small planet is our Earth. Its pole crowned with a circle of northern lights. The whole planet glowing in the infrared warmth of a star we call Sun. A tiny new spacecraft called TRACE brings us a view of the Sun that is still largely beyond the scope of our understanding. Magnetic field lines burst through the surface to unleash in seconds as much energy as the world uses in a million years. It has shone for 5 billion years and will shine for 5 billion more. For us, it is the great engine of life.